Okay, is it the screen is visible to all? Hello.
Yes, sir.
So good afternoon to everyone. In the last lecture, we seen that what is the definition of linear transformation. Okay, the linear transformation is also called as vector space homomorphism. Okay, let V and U be the vector space over the same field K. Then any map that T from V over K to U over K is the linear map if T of U plus V is equal to T of U plus T of V, and T of A plus U is equal to A into T of U, where U and V, these are the two elements, belongs to the vector space, and A, small a, belongs to the capital K. Okay, or instead of going to this two, combine these two conditions in one, that is T of AU plus BV is equal to A into T of U plus B into T of V, where U and V belongs to capital V and A and V belongs to capital K. Okay. Now, in the other words, we can say that the first condition is called as vector addition, and second condition is called as scalar multiplication. Okay, and all these words are equivalent to each other. Linear transformation is equal to linear mapping. Also, it called vector space homomorphism or linear function. And also, we've seen that some examples. Identity transformation is a linear transformation. Second word, zero transformation is also linear transformation. Third one example is differential of letter, the derivative of a polynomial. Okay, if we be the vector space of all the polynomial in the variable x, then the d from v to v defined by d by dx of f of x is also a linear transformation, and it also called as differential operator. And the last example, fourth one is integral transformation. Okay, if we be the polynomial, the vector space of a polynomial in the variable x, and are defined by v to v such that I of f of x is equal to integration 0 to t f of x. It also satisfies the two conditions of linear transformation. Okay, hence this operation is called as again linear transformation, and that linear transformation is called as integral transformation. Okay, and also we see that this one example. F of x is equal to ax, where A is the fixed matrix of order m plus n. Okay, also the linear transformation. Okay, so today we will see one more definition. What is vector space isomorphism? Definition of vector space isomorphism. Write down this name. Vector space isomorphism. Okay. Now look at the definition of vector space isomorphism. Definition. Let V over F, capital V over F, and capital U over F, okay, be vector spaces. Vector spaces. Okay, then a linear map. The map is a linear transformation. What is F from capital V to U? Okay, it's called vector space isomorphism. The mapping is called as, if it is a linear, okay, first F is a linear map. This one. This is linear transformation. It's called the vector space isomorphism if this function f is 1 1. Okay, and on 2. Okay, f what is the function f is what? 1 1 and on 2. That means every element of v corresponds to every element of u. One-to-one correspondence is there in between v and u, and the range set of f is equal to whole vector space u. Okay, that means the function is onto. What is a vector space isomorphism? Let v over f and u over f be a vector spaces, a linear map f. F is must be a linear. Okay, remember it. F is must be the linear map. It's called the vector space isomorphism if f is 1, 1 and onto. Okay, now so that is to say any map. Okay, suppose f is the any map from V to capital V to capital U. It's called vector space isomorphism. Vector space isomorphism. If and only if first one f is 1, 1. Okay, or we can say this is all the definition of vector space isomorphism. Second one is capital F is onto. Okay, and third one is capital F is linear transformation. Linear transformation. What is the meaning of linear transformation? That is f of AU plus BV is equal to f A into f of U plus B into f of small. Okay, where U and V, these are the elements for all U and V belongs to capital V, and small a and small b belongs to the field F. Okay, from field F. Okay, so this is the definition of vector space isomorphism. So in this case, we also say that capital V is isomorphic. Capital V is isomorphic to capital U. Okay, and it is denoted by V is isomorphic to U. Okay, any doubt in the definition of vector space isomorphism? Okay, so this is the definition of vector space isomorphism. F is 1, 1, F is onto, and F is linear transformation, then that V is isomorphic to U. Okay, now the next definition, what is the null space? Okay, the one more important topic of our syllabus, null space. Okay, or we can say that kernel of a linear transformation. The null space is also called as kernel of a linear transformation. Okay, null space or kernel of a linear transformation. Okay, now look at the definition. Let capital V over F and capital U over F be two vector spaces. Okay, let capital V over F and capital U over F be the two vector spaces over the field F, and let T is the mapping or T is the function from V to U. Be a what? Linear map. This function is what? Linear transformation. That means it satisfies the two conditions, vector addition and scalar multiplication. Okay. T is the function from V to U via linear transformation. Then the set capital S of all those elements, of V. Okay, take the element from the V. Okay, set is what? All those elements of V which are mapped onto the zero vector. Okay, zero vector zero dash of U. Okay, so it's called, that set is called yes. Okay, and the yes is called what? The kernel of the homomorphism T. Okay, why we can say that homomorphism? Because linear transformation is also called as vector space homomorphism. Okay, so that is the linear transformation is also called as vector space homomorphism. That's why here kernel of the homomorphism T, or kernel of the linear transformation T, we can say, and it's denoted by, KER, kernel of T. Okay, or we can write this as a N of T, null space of T. Okay, so what is the definition of null space? Let V over F and U over F be the two vector spaces. Which T from V to U be the linear transformation. That is vector space transformation. And the set yes. What is the set S? All those elements of V. Okay, taking the collection of those elements belongs to capital V, which are mapped onto the zero vector, okay, of U, zero vector of our codomain. Okay, if we apply T of X belongs or is equal to 0, then X is the element of S, and S is called as kernel of the homomorphism, and it is denoted by kernel of T or N of T. What is N of T? Null space of that linear transformation. Okay, so by symbolically we can write the set yes. Okay, what is the set yes? Look at here. So here the set yes is equal to N of T is equal to yes is equal to, we can say that N of T. Okay, we also can write kernel of T, which is equal to collection of a set hai na? So this is the set yes, all those elements of V. Okay, take the elements belongs to capital V. Okay, that is X belongs to capital V, such that if you apply T, okay, apply mapping T, then T of X is equal to what? Which mapped, sorry, this is mapped onto zero vector. Okay, zero dash of output would need तुमचा V U मध्ये. Okay, so zero vector of U. Okay, so this is equal to null of T means what? Null space of capital T. Okay, so this is the definition of what? Null space of T or kernel of homomorphism. Okay, on the later on we are going to prove that the null space of T is the vector subspace of this null space of T. This N of T becomes a subspace of V. Okay. In this null space, there is a collection of the elements from V. So this is the subspace of V. We are going to prove on the later on. Okay. So here, remember only definition. Yes, it's equal to null space of T is equal to, or kernel of T is equal to what? Collection of those elements belongs to V. If you apply T, or mapping T on that element X, then it becomes zero element of that codomain, that is U. Okay, that is X belongs to V such that T of X is equal to 0 dash, where 0 dash is the what? Zero element of U. Now look at some example. First one. If T is the mapping, let T is the mapping from R2 over R to again R2 over R. That is, here the U and V are same. Be a map. Be a map defined by wait a minute. Okay, R2 over R. T is the mapping from R2 over R from R2 over R. Defined by T of X and Y. Okay, here the element belongs to R2 over R means what? Ordered pair. So apply the T on that ordered pair X, Y. Okay, it's equal to X and 0. This is the mapping which is given to us. Okay, where X and Y, these are the element. This is the element belongs to R2 over R. Then show that T is this T is linear map or linear transformation. Okay, and find its range and null space. Okay, the range of that linear transformation we find later on. First, we have to show that this T is linear transformation, and we have to find the null space of that T. Okay, now look at the solution. What is solution? Let here domain is R2. Okay, and codomain is also R2. Every element belongs to R2 is of the type X and Y. Okay, ordered pair असेल. तुमचा हा एक element नसेल X, ordered pair मध्ये असेल R2. So let U is equal to X1, Y1. Okay, and small v is equal to X2, Y2. This is the two elements belongs to what? R2. Okay, over R. And take A and B. These are the two scalars belongs to R. Okay, this R. We have to show that T is linear. First one. What is the linear map? If you have to show that T is linear, you have to show that what? To prove that T of A into U plus B into V is equal to A into T of U plus B into T of V. Okay, you have to prove that. To prove that T of AU plus BV is equal to A into T of U plus B into T of V. Okay, consider A into U plus B into V. Okay, first find out what is this element. No, this is A. What is U? X1, y1. Okay, plus what is b? B into what is your v? X2 y2. Now this one is what? ax1 plus b, sorry, ax1, I don't know, a y1 plus bx2 b y2, which is equal to ax1. Now addition of these two vectors, ax1 plus bx1, comma ay1 plus by2. Okay, first coordinate addition with first coordinate of second vector, and the second coordinate with second coordinate. So here we get what is au plus bv, ax1 plus bx1, comma ay1 plus by2. Now apply t on both sides. T of au plus bv is equal to t of ax1 plus bx1, comma ay1 plus b, sorry, here extra line, excuse me. Sorry. Wait, but what is t of x0? T of xy, which is equal to what? X comma 0. So first coordinate is as it is, and second coordinate becomes 0. Okay. In the example, the question given that the x term is as it is there, and the y coordinate becomes 0. Applying t on the vector xy, the first coordinate is as it is there, x transformed to x, y transformed to 0. So here, if you apply t on this element, so first coordinate is as it is, ax1 plus bx2, and second coordinate becomes 0. Okay, so now this is equal to ax1, wait a minute, plus bx2. This is, we can write 0 is 0 plus 0, which is equal to ax1, write down this one, plus 0, sorry, ax1 comma 0 plus bx2 comma 0. Okay, so this vector we can write like this. Okay, so which is equal to, take a to outside this one, a into x1 comma 0 plus b into x2 comma 0, which is equal to a into what is this one? E of xy, x1, y1. Okay, plus b into t of x2, y2, which is equal to, this is a, what is x1, y1? U. So this is t of u plus b into what is x2, y2? T of v. So here we get on the left hand side, t of au and plus bv is equal to t of au plus pv is equal to what? A into t of u plus b into t of v. Okay, so hence t is a linear transformation. Any doubt up to here? Okay, so here the t is linear transformation.
No,
Now
sir.
you have to find the range space. Sorry, range of that. Find its range. The range we find later on. First, we have to find the null space. Okay. After the definition of, after seeing the definition of range space, we can we define that one. Okay. Now here the first define the null space of the linear transformation. Second one, null space of T. What is null space of T? By the definition of null space of T, collection of elements belongs to R2 over R, such that if we apply T on that element, it becomes zero element of codomain, that is R over R. So here the codomain, zero of the codomain is what? 0, 0. Okay, so which is equal to, this is the definition of null space, collection of the domain taking the X element from the domain, such that if you apply the T on that map element, we get 0 of the codomain. Okay, so this one. So here X, Y belongs to R2 over R, such that what is T of XY? T of XY is given by T of X and sorry, T of XY is equal to what? X0. Okay, by the mapping which is given to us, which is equal to 0 and 0. Okay, so this is equal to XY. Okay, here the domain and codomain is same. Domain is R2, codomain is R2. So here no need to write R2 or R. Collection XY, the ordered pair XY, such that by the what we get here, by the comparing the coordinate, first coordinate, what we get here, X is equal to 0 and Y is any element. ओके, y काही का असेल तुमचा, तो काय होणार असेल, 0 होता है. ओके, सो y बिलोंग्स टू R. Okay, so this is equal to, now put X is equal to 0 here, 0, and Y is arbitrary, such that Y belongs to R. Okay, so element of the type 0Y is the what? Null space of T. Okay, element of the type 0 and Y. कोणताही element 0Y. Okay, 0, Y1 is element असतील. This is the type of the null space of T. These are the types of the elements of null space of T. Okay, for example, look at this one. If suppose take the element 0 and 5. Okay, from collection of R2 over R. Okay, this is the element from R2 over R. Now if we apply T on this element, okay, what we have, T of X, Y is equal to what? 0, sorry, X and 0. X term is as it is there, and Y terms must transform to 0. Okay, so here what is X? 0. So X term is as it is there, 0, and Y terms must be transformed to 0. And now look at here, this is the element of what? 0 vector of R2 over R. Okay, कोणते element घ्यायचं? Look at this one. Suppose 0, minus 7. This is the element from R2. If we apply the image transformation on this element, so X coordinate as it is. What is X coordinate here? 0. So this is as it is. And Y coordinate is minus 1. But minus 1 transformed to 0 by our mapping. Okay, so now this one is what? 0 vector of R2 over R. So element of the type 0Y. Okay, the element of the type 0Y is the null space of T. Okay, any doubt? Any doubt up here? So this is the definition of null space. Okay, now we will see what is the range space. Okay, any doubt up to here? Give me reply. Hello. Okay, now the next definition is the range space of a linear transformation.
No doubts.
Now
so we have not calculated the range,
you have to see the definition of range space. Okay, the next definition is range space. Okay, after seeing the definition of this one, we calculate. Okay, we calculate the range space of T. Okay, now definition of range space of a linear transformation. Okay, now look at the definition. Let T be a linear transformation. Let capital T be a linear transformation. Okay, let T be a linear transformation from vector space V over F. Vector space V over F into vector space U over F. Okay, then the range of T, the range of T is defined as the image set of V under the mapping T. Okay, and it is denoted by range of T, that is R of T. Okay, what is R of T? Range of T. What is N of T? Null space of T. R of T, range space of T, range of T. Okay, or we can say that image space of T. Okay, so symbolically we can write we have the range space of T is equal to image of T. Okay, what is that said? All the images under the T. Okay, let T be the linear transformation from the vector space V over F to U over F. That is, T is the mapping from capital V to capital U. Okay. Now, what is the range of T? Taking the images of all the elements of V. Okay, that is, so images are said T of V such that small v. Okay, this is small v. Small v belongs to capital T, which is equal to range space of capital T. Okay, so this is the definition of range space. The let T be the linear transformation from vector space V over V to U. The range space of T is nothing but what? Image set of V. That is, images of all the elements from the set V under the mapping T, and it is denoted by R of T, or images of T, or image space of T, which is equal to T of V, where V belongs to capital V. Okay, now we can find the range space of that T. Okay, third one. What is third one? Range space of T. Okay, that is R of T. By the definition of R of T, we have T of small v, where small v belongs to capital V. Okay, and T of x0, xy is given by x is transformed to as it is x and y is transformed to 0. Okay. So T of x, by the definition, in the question, it is given that T of xy is equal to x0. Now find the range space of T. Now T of, what is V here? Ordered pair. T of xy such that x and y belongs to capital V. Okay, that is capital V is what here? R2 over R. Okay. Which is equal to what is of T of xy? is x0. So as right there, x0 such that x and y belongs to R2 over R. Okay, so element of the type x0 are the range space of. Okay, so this implies what we have there, this x0 such that x and y belongs to R2 over R. Okay. x0 म्हणजे काय येईल, suppose in order way. So this is the range space. The element of the type x and 0. The first coordinate is arbitrary and second coordinate is 0. Okay, now look at this one. Suppose this is x-axis. This is y-axis. Okay, so this is the element. Suppose this is 1 1. Okay, now this 1 1 is not the range space. Why? Because the second coordinate here not 0. Okay, मग second coordinate 0 कधी येईल माझा? Suppose that my point is here. Okay, now suppose this is the 2 0. Okay, now this point is in my range set or range space. Also, this point, suppose this is minus 2 0. Okay, now second coordinate is 0. First coordinate is arbitrary. You can take any point at first coordinate. So our range space here is nothing but our whole x-axis. On the x-axis, every element of the type what? x0. Is it clear? Okay. x-axis होता कोणताही पॉइंट घ्या तुम्ही, तो काय असेल? Suppose it's -5. The second coordinate must be 0. Okay. पण हा पॉइंट असेल -2 -3 5. Okay, for example, the second coordinate not 0. So this point not in that set. Okay, that means this point is not in the range set of T. Okay, any doubt now? Okay, so this is the range space. Now we have to show that this range space, range of T, and the null space of T, these are the two subspaces of Q and V. Okay, T of U, T of U, this element must be belongs to U, domain, codomain. Okay, and in the null space, look at here, in the null space, by the definition of null space, these are the subspace of subset of V. Okay, in the later on, we have to show that this n of T is the subspace of capital V, and R of T is the subspace of capital U. Okay. Wait a minute. So this is what range of T. Okay, any doubt up to here? Now, the next one is next type of transformation, singular transformation. What is meant by singular transformation? Okay, the next definition is singular and non-singular transformation. We know that zero transformation, identity transformation, differential transformation, or integral transformation. Now this type is singular transformation. Okay, now look at the definition. Let V over F, V over capital F, and U over capital F, okay, be vector spaces. in vector spaces over over a field F, over a field capital F. Okay, a linear transformation. A linear transformation. T from V to U. Okay, is said to be. Is said to be singular. Said to be singular if and only if there exists x not equal to 0 belongs to instead of writing this one, wait a minute, write this 0 not equal to x, that is non-zero element from the domain, okay, that is V, such that if we apply t on that element x is equal to 0. Okay, what is the meaning of this one? So there exists an element x belongs to V which is not equal to 0, but their image is 0. Okay, their image is 0. Then that transformation is called as singular transformation. Now look at the example here. So here they given that t of xy is equal to x0. So here there exists a non-zero transformation, non-zero element. Okay. This is the non-zero element, 0 and y. Okay. Which is not equal to 0, 0. What is the zero element of R2? 0, 0. Okay. So this is not equal to 0, 0. But you apply t on this element. So x as it is there. Okay. By the definition of t, x coordinate as it is 0 and y transform to 0. So here 0y is not equal to 0, 0, but t of 0y is 0, 0. Hence this transformation, which one? T of xy is equal to x0 from R2 to R2 is the singular transformation. Okay. What is the singular transformation? There exists at least, suppose at least one element there exists like this, which is not equal to 0 belongs to V, but you apply the transformation on an element, then it must be 0. Then that transformation is called as singular transformation. Okay, that is if and only if the image of some non-zero vector, okay, the image of some, this is non-zero vector, okay, of capital V under the map T, under the map T is the zero vector. Zero vector. That is, x is not equal to 0, but you apply the mapping, apply the t on that element x, then it becomes 0. Then that transformation is called as singular transformation. And the next one is non-singular transformation. The next definition is what? Non-singular transformation. Okay. Definition. Let again V over F and U over F be vector spaces. Okay, a linear map. A linear map T from V to U is said to be non-singular. singular. Okay, it's said to be non-singular if only 0 belongs to V. Okay, maps into 0 belongs to U. Okay, that is, what is the meaning of this one? If the kernel of T, that is equal to null space of T, which is equal to singleton 0. Okay, symbolically we can write, symbolically T is non-singular. T is non-singular if and only if T of small v is equal to 0, where this V belongs to capital V, implies V must be 0. Okay, small v must be 0. This is not the capital one, small one. Okay, or if x is not equal to 0, then it implies T of x also not equal to 0. Okay, so this is the definition of singular transformation. What is the singular transformation? If T is the mapping, if T is the linear transformation from V to U, is said to be non-singular if only 0 vector maps to 0. Okay, that means you apply T on only 0. Okay, T, apply T on the 0 element of V, then it becomes 0. That is, kernel of T is equal to singleton 0. What is kernel of T? Kernel of T is that is null space of T. We seen that. Okay, what is kernel of T, null space of T? Collection of those elements of V which maps to 0 element of U. So here, this is the only element of V which maps to 0 on 0 of VU. Okay, so if kernel of T or null space of T contain only 0 vector, then that transformation becomes a non-singular transformation. Okay, or this definition we can write, if T is the non-singular if and only if. Okay, when this T becomes a non-singular, if T of V is equal to 0, जर T of small v is equal to 0 असेल तर तो V itself 0 असायला हवा. ओके, याचा निगेशन घेतलाय त्याचं. Okay, that is, if x is not equal to 0, T of x is not equal to 0. Okay, what is the negation of this one? T of x is equal to 0, then x is equal to 0. Okay, so this is the definition of non-singular transformation. Okay, again look at here. What is non-singular transformation? The kernel of T or null space of T contain only 0 element, then that singular transformation is called as singular or non-singular transformation. Okay, any doubt up to here? Okay, so for today it is sufficient now. Wait a minute.